Millions of years before humans appeared, the Earth was home to a different kind of ruler, the dinosaurs. They were creatures of astonishing variety and scale, towering giants that shook the ground with every step, nimble hunters that darted through forests, and even tiny feathered beings that glided through prehistoric skies. For over 165 million years, they thrived across every continent, adapting to changing climates and landscapes as the planet itself evolved. Though they vanished long ago, their fossilized remains still speak across time, telling a story of power, survival, and transformation. To study dinosaurs is to peer into the deep past, to witness nature's boundless imagination at work, and to glimpse the roots of life as we know it today. When people think of dinosaurs, they often imagine towering creatures like the long-necked Brachiosaurus or the ferocious Tyrannosaurus rex, beasts so enormous that they seem to belong to another universe entirely. Yet the truth of their existence is far more varied and intricate. Not all dinosaurs were giants. Many were small, nimble, and light-footed, living lives that demanded speed, cunning, and adaptability rather than brute strength. Some were scarcely larger than modern birds, their bones delicate as reeds, their movements swift as flickering shadows beneath the ancient sun. The world of the dinosaurs was not simply one of giants, but a vast and complex tapestry woven with creatures of every conceivable shape and size. In the dense undergrowth of the Mesozoic forests, small dinosaurs darted between ferns and cycads, their sharp eyes always watchful. These were creatures like Compsognathus, a lithe predator no longer than a house cat, hunting insects and small reptiles. There were tiny herbivores too, such as Lesothosaurus, who lived by stealth and alertness rather than by the protection of great size. These smaller species occupied niches that their gigantic cousins could not, surviving on what the giants overlooked, thriving in places where massive feet could never tread. Their lightness was their strength. They could hide, sprint, and adapt to the changing moods of their ancient world. As evolution unfolded, the small dinosaurs began to experiment with new ways of living. Some developed feathers, not for flight at first, but for warmth and display. Feathers became an armor of color and texture, perhaps used to attract mates or to camouflage against predators. Among these feathered forms were creatures like Microraptor, a crow-sized dinosaur with shimmering plumage and 4 wings that allowed it to glide through the air. Others, such as Velociraptor, combined speed and intelligence in ways that made them formidable hunters despite their modest size. The fossil record suggests that some of these smaller species lived in groups, communicating and hunting cooperatively, revealing a social complexity that would one day echo in the behavior of birds. Their smallness also made them remarkably adaptable. When climates shifted or food sources dwindled, the giants often struggled to adjust, their enormous bodies demanding constant sustenance. But the small dinosaurs could endure scarcity by changing their diets or migrating to new regions. They were flexible, quick to evolve, and able to seize opportunities that others could not. In the grand story of survival, these qualities mattered as much as strength or size. Over millions of years, they quietly outlasted countless larger species, proving that survival favors those who can change. The diversity of small dinosaurs also hints at the beginnings of something entirely new, the evolution of flight. From their ranks arose the first true birds, delicate yet resilient, creatures that carried the legacy of dinosaurs beyond the reach of extinction. The same light bones and feathers that once gave them agility on the ground and in the trees became tools for conquering the sky. When the age of the dinosaurs ended in cataclysm, these descendants took wing and continued the story in another form. Every bird alive today, from a sparrow to an eagle, carries within it the spirit of those small survivors. To understand that not all dinosaurs were giants is to appreciate the extraordinary adaptability of life. The Mesozoic world was not just a stage for massive creatures to thunder across the land. It was also a place of quiet, intricate dramas played out by animals that could fit in the palm of a human hand. They chirped, darted, hunted, and hid among the roots of trees that have long since turned to stone. Their bones remind us that nature does not only celebrate the colossal, it also perfects the small, the quick, the subtle. In their fragile remains lies the proof that life's success is not measured in size, but in resilience, imagination, and the ability to endure across time's shifting landscapes. Dinosaurs, the mighty rulers of the Mesozoic era, did not all grow at the same pace. Just as in today's animal kingdom, where a mouse matures within months while an elephant takes years to reach full size, dinosaurs exhibited a remarkable variety of growth rates. Some shot up to their adult forms with astonishing speed, while others took their time, stretching their growth over decades. This diversity in growth patterns reveals not only how complex dinosaur biology was, but also how adaptable these creatures became in their struggle to survive across millions of years and countless environments. Fossilized bones provide the key to this ancient mystery. When paleontologists slice through a dinosaur bone, they sometimes find growth rings, much like those inside a tree. Each ring represents a year of life, recording the rhythm of growth spurts and pauses caused by seasonal changes or food scarcity. By counting and studying these rings, scientists can estimate how fast a dinosaur grew and how long it lived. From these clues, a fascinating picture emerges. Some dinosaurs reached adult size within just a few years, while others grew slowly and steadily over much longer spans of time. Take, for instance, the enormous sauropods, the long-necked giants such as Apatosaurus or Brachiosaurus. Despite their titanic size, some weighing as much as a dozen elephants, they didn't take centuries to grow. Instead, they likely reached their adult mass within 20 or 30 years, an astonishing pace for such enormous animals. Their bones show signs of rapid, uninterrupted growth, suggesting that once they hatched, they rarely stopped eating or expanding. Constant feeding, fueled by vast quantities of vegetation, allowed them to outgrow most predators quickly. Speedy growth may have been their greatest defense, turning vulnerable hatchlings into colossal adults that few creatures dared to challenge. In contrast, some smaller dinosaurs, especially early or more bird-like species, appear to have grown more slowly. Certain theropods, the group that includes Tyrannosaurus rex and the ancestors of modern birds, show evidence of fluctuating growth rates, speeding up in times of plenty and slowing down when resources were scarce. For example, a young T. Rex may have gone through growth spurts during adolescence, doubling its weight in just a few years, but earlier in life its growth was steadier, allowing it to conserve energy. This pattern suggests a flexible metabolism, able to adjust to environmental pressures, an advantage in a world often shaken by changing climates and competition for prey. Even among dinosaurs of similar size, growth could vary dramatically. Two species that lived side by side might have taken completely different paths to adulthood depending on their diet, environment, or physiology. Some herbivores, for instance, may have grown slowly to conserve energy while maturing steadily, relying on herds for protection rather than speed or size. Others, like the duck-billed hadrosaurs, grew at an impressive rate, reaching maturity quickly to reproduce before predators or harsh conditions could cut their lives short. These differences in growth also reflect the deep evolutionary transitions occurring within the dinosaur lineage. Warm-blooded traits, such as faster metabolism and active lifestyles, emerged in some groups, while others retained more reptilian, cold-blooded characteristics. This means that the line between fast-growing and slow-growing often mirrors the line between bird-like and reptile-like ways of living. Dinosaurs were not uniform in how they functioned. They were an evolutionary mosaic, each adapting to its own ecological niche. Understanding how dinosaurs grew tells us more than just how big they were. It tells us how they lived. Growth rate determined everything from their survival strategies to their social behavior. Fast-growing dinosaurs may have needed to eat constantly, roam vast territories, or live in herds for protection and access to food. Slower-growing species may have relied more on camouflage, endurance, or parental care. Each pace of growth was a reflection of a world teeming with challenges, where time itself was a test of survival. In the end, the story of dinosaur growth reminds us that evolution is not a race towards size or speed, but a delicate balance of life's possibilities. Some dinosaurs lived fast and grew faster, while others took the slow road to adulthood. Yet all of them, in their own time and way, filled the earth with life so varied and vibrant that their legacy still echoes in the bones they left behind, and in the beating hearts of the birds that carry their story forward today. For more than 165 million years, dinosaurs dominated the earth in a reign that spanned vast stretches of geological time, from the late Triassic period through the Jurassic and into the end of the Cretaceous. To imagine that scale is almost impossible. It is longer than the entire span of human existence by an immeasurable margin. Our own recorded history fits into only a sliver of time compared to their era. Dinosaurs were not brief visitors on the planet. They were the planet's great experiment in life, adapting, thriving, and diversifying in ways that changed the course of evolution forever. In the beginning, they emerged quietly, evolving from small, reptilian ancestors that shared the world with many other creatures. There was no single moment when dinosaurs appeared as the mighty giants we picture today. They started as modest beings, slender and quick, competing for survival in harsh landscapes. Over millions of years, natural selection shaped them into a stunning variety of forms, some towering as high as trees, others no larger than chickens. They walked on two legs and flew through the air, and swam in ancient seas. Their world was a living laboratory of adaptation and transformation, and they mastered it completely. Through the Jurassic period, the Earth was lush and green, filled with vast forests and humid swamps. It was an age when life seemed to expand in every direction. Massive herbivores like Brachiosaurus and Diplodocus roamed the land, their necks reaching for leaves that grew high above the ground. Carnivorous hunters such as Allosaurus followed, balancing the ecosystems with the constant rhythm of predator and prey. In this long stretch of stability, dinosaurs became the most successful creatures to ever live on land. They filled every possible niche. Some evolved to graze, others to stalk, others to soar. What makes their story so extraordinary is not just their dominance, but their endurance. The Earth itself changed repeatedly beneath their feet. Continents drifted, oceans opened and closed, climates shifted from steamy jungles to dry deserts. Entire mountain ranges rose and eroded again, yet dinosaurs continued to thrive through it all. They survived mass extinctions that wiped out other species, enduring through adaptability and resilience. Theirs was a tale of patience and persistence written across millions upon millions of years. Even the smaller, seemingly insignificant dinosaurs played a role in this grand story. The early bird-like creatures that flitted through Cretaceous skies were not just fleeting curiosities. They were ancestors of today's birds, living reminders of that ancient world. Every sparrow or eagle alive now carries within it the legacy of creatures that walked among giants. In that sense, dinosaurs never entirely vanished. Their bloodline still beats in wings that flap across our skies. When their long dominion finally ended around 66 million years ago, it was not gradual. A catastrophic event, most likely a massive asteroid impact, brought a sudden fiery close to the age of dinosaurs. The skies darkened, temperatures plummeted, and ecosystems collapsed. For all their strength and adaptability, they could not withstand the speed and violence of that global catastrophe. The Earth turned a page in its deep history, and mammals, small, shrewd survivors, rose to fill the empty spaces they left behind. To think that dinosaurs lived for over 165 million years is to confront the scale of deep time and our smallness within it. Their world stretched across epochs, continents, and climates, a saga longer than imagination can truly grasp. Compared to their reign, humanity's time on Earth is barely the blink of an eye. Yet their fossils, preserved in stone, speak to us across that immense gulf. They remind us that life endures, transforms, and sometimes vanishes, but always leaves traces for those who come after. The story of the dinosaurs is not just a tale of ancient creatures. It is a testament to the vast, restless creativity of life itself. The world of the dinosaurs was not silent. It was alive with sound, low rumbles that carried across open plains, sharp calls that echoed through forests, and perhaps even musical notes that resonated beneath ancient skies. Though we can never hear them directly, the evidence left in fossils and bone structures suggests that many dinosaurs could communicate, using their voices and bodies to share warnings, attract mates, guide their young, or maintain the delicate balance of life within a herd. They lived not as mute giants, but as expressive creatures whose sounds and gestures helped shape their survival. Some of the most striking clues come from the hadrosaurs, often called duck-billed dinosaurs. These plant-eating creatures had elaborate, hollow crests on their heads, shaped like long tubes or helmets. Scientists believe these crests acted as natural sound chambers, amplifying their calls much like a musical instrument. When air passed through, the crests could have produced deep, resonant tones that rolled across the landscape. Each species had its own unique crest shape, suggesting that their calls too were distinct, perhaps allowing them to recognize one another across great distances. It is easy to imagine a herd of hadrosaurs moving together, their voices blending into a chorus that could be heard for miles, announcing their presence or keeping the group together. Communication likely took many forms beyond sound. Some dinosaurs used sight as their primary language, displaying color, movement, and posture to send messages. Fossils and comparisons with modern birds suggest that many species were covered not just in scales but in feathers, some brightly colored. Feathers could have served as visual signals, flashed during courtship, raised in threat, or spread wide to assert dominance. Even large herbivores might have used movement and stance to communicate, raising their heads or swinging their tails as warnings to others. Predators, on the other hand, may have relied on subtler forms of expression, communicating with body language or scent while coordinating hunts or establishing territory. The social nature of many dinosaurs also supports the idea that they communicated regularly. Fossil trackways showing herds of adults and juveniles moving together suggest coordination and care, which would have been impossible without some form of signaling. Mothers may have called softly to their newly hatched offspring, guiding them to safety. Herd members could have used low-frequency sounds, vibrations too deep for the human ear, to stay in touch even when separated by distance or thick vegetation. Some of these sounds might have traveled through the ground itself, much as elephants communicate today. To survive in groups, they needed to share information, and evolution gave them the tools to do so. Even the great predators likely had their own voices. The structure of their skulls hints at resonating chambers and flexible throats that could have produced growls, roars, or hisses. A Tyrannosaurus rex may have announced its presence with a deep, earth-shaking sound rather than the high-pitched roar popularized by movies. These low-frequency noises could travel far, warning rivals and asserting dominance over territory. In a world of constant competition, communication was not only useful but essential, a way to avoid unnecessary fights and conserve energy for the hunt. When we consider dinosaurs as communicative beings, they begin to feel more alive, more complex than the silent skeletons displayed in museums. Their world was one of interaction and awareness, a dynamic environment filled with messages constantly sent and received. Whether through sound, color, posture, or movement, they spoke a language of survival, one written into their very anatomy. Their communication connected them to each other and to the living pulse of their ecosystems. Though we will never hear the true voices of the dinosaurs, the evidence tells us enough to imagine them. A chorus of calls rising over the primeval landscape, the deep rumble of a warning, the rhythmic beat of a crest's vibration. In those echoes of sound and movement, we glimpse creatures that were not just massive or fierce, but social, emotional, and aware of one another in ways both ancient and profoundly familiar. The image of dinosaurs often conjures thoughts of immense creatures thundering across the land, their heavy feet stirring clouds of dust beneath ancient skies. Yet the Earth of the Mesozoic era was not only a world of plains and forests. It was a planet crisscrossed by rivers, lakes, and shallow seas. In these watery realms, some dinosaurs found not barriers but opportunities. Evidence now shows that several species could swim, their bodies and behaviors adapted to the fluid, shifting element of water. They were not limited to dry land but moved with ease between worlds, gliding through currents as naturally as others walked the earth. Tracks preserved in stone reveal their aquatic abilities. In sandstone beds once part of ancient river systems, paleontologists have discovered patterns of claw marks made by dinosaurs as they paddled through shallow water. The impressions show rhythmic, alternating strokes, clear traces of swimming motion. These fossils tell of creatures that did not fear the water but entered it deliberately, perhaps to cross a channel, escape a predator, or search for food. Their buoyant bodies and strong limbs allowed them to propel themselves forward, their tails swaying gently behind them for balance. In these quiet moments, the giant rulers of the land became graceful swimmers. Among the most famous aquatic adapted dinosaurs was Spinosaurus, a predator unlike any other. With its elongated snout filled with conical teeth, reminiscent of a crocodile's, and its dense bones that helped it stay submerged, Spinosaurus was a master of the waterways. It lived in what is now North Africa, in a landscape of vast deltas and winding rivers. Fossil evidence suggests it hunted fish and other aquatic prey, paddling with strong hind limbs and steering with its powerful tail. Its sail-like spine rose above the water's surface, perhaps glinting in the sunlight as it swam through the reeds. In Spinosaurus, evolution had created a true semi-aquatic dinosaur, one that blurred the line between land and water in remarkable ways. But Spinosaurus was not alone. Smaller theropods, such as baryonyx, also showed adaptations for swimming and fishing. Its long claws and narrow jaws made it an efficient hunter of river life. Even herbivorous dinosaurs may have entered the water to feed on aquatic plants or to cool themselves in the heat. The mighty sauropods, with their massive bulk, might have used rivers and lakes to support their weight while crossing floodplains, their long necks rising like periscopes above the surface. Though they were not swimmers in the true sense, they were comfortable in the shallows, their movements steady and deliberate as they waded through the ancient wetlands. The ability to swim was not merely a curiosity. It was a survival advantage. Waterways offered safety, food, and pathways to new territories. In a world of predators and changing climates, those dinosaurs that could navigate the water gained a vital edge. The young may have learned to paddle early, instinctively finding refuge in rivers when danger loomed. For others, the water was a hunting ground, a place of opportunity where agility and strength replaced sheer size as the measure of success. The thought of dinosaurs swimming, of massive bodies gliding through prehistoric lakes or nimble predators chasing fish beneath the surface, expands our understanding of their world. They were not confined to one way of life, nor defined solely by the land they walked on. Their adaptability was immense, their behaviors as varied as the ecosystems they inhabited. the fossilized trackways, the specialized bones, and the preserved teeth all whisper of a time when rivers shimmered with movement, when ripples spread from the strokes of creatures that once ruled the earth. To imagine these ancient swimmers is to see dinosaurs not as rigid, lumbering beasts, but as vibrant, dynamic beings fully engaged with the richness of their environment. They belonged as much to the water as to the land, and their legacy, preserved in stone and sediment, reminds us that life has always been drawn to the shifting boundaries between worlds, where land meets water and survival demands both strength and grace. Among the many remarkable traits of dinosaurs, one of the most intriguing was their ability to regenerate teeth. Unlike humans who must make do with just two sets, baby teeth and adult teeth, many dinosaurs could replace their teeth throughout their lives, growing new ones as old ones broke, wore down, or fell out. This continuous renewal gave them a powerful evolutionary advantage, especially in a world where survival depended on the constant struggle to feed, fight, and endure. Each fresh tooth was a sign of resilience, part of a biological system perfectly adapted to the harsh realities of prehistoric life. The fossil record reveals that dinosaurs' teeth varied widely depending on diet and lifestyle. Carnivorous theropods, like Tyrannosaurus rex and Velociraptor, had sharp, serrated teeth designed for slicing flesh and crushing bone. Herbivorous species, such as Triceratops or Hadrosaurus, bore flatter teeth suited for grinding plants and tough vegetation. But no matter their shape or purpose, these teeth faced tremendous wear. Meat-eaters bit into bone and muscle, often chipping or losing teeth during feeding. Plant-eaters ground their teeth against fibrous stems and gritty leaves, slowly eroding them over time. To deal with this, nature equipped many dinosaurs with a built-in solution: a lifetime supply of replacements. Scientists studying fossilized dinosaur jaws have found clear evidence of tooth regeneration. Within the jaws of many species are rows of developing teeth waiting just beneath the surface, like a conveyor belt of replacements. When one tooth fell out or wore down, another from below would rise to take its place. In some species, this process happened astonishingly fast. For example, Majungasaurus, a predatory dinosaur from Madagascar, replaced its teeth roughly every 2 months. In contrast, some herbivores regenerated teeth at a slower but steady rate, maintaining a continuous grinding surface for their plant-based diets. This ability was made possible by specialized stem cells located in the dental tissue, similar to those seen in modern reptiles like crocodiles and lizards. Crocodiles today can grow new teeth throughout their lives, a trait inherited from their distant dinosaur relatives. These stem cells triggered the formation of new teeth in a cycle that never truly ended. As one tooth reached the end of its usefulness, another was already forming beneath it, ensuring that the animal was never left without its vital tools for eating and defense. For large carnivores, this regenerative ability meant they could afford to be brutal eaters. A T. rex might snap its own teeth while crunching into bone, but that was no real concern. New ones would soon take their place. Some fossils even show replacement teeth at various stages of development, layered within the jaw like nested shells. The system was efficient, constant, and crucial for survival in a world where every meal could be a violent struggle. In herbivores, the process evolved differently but served the same purpose. Dinosaurs like Diplodocus or Nigersaurus had batteries of teeth that worked together, grinding enormous amounts of plant matter each day. Their teeth wore down quickly under the strain of constant feeding, yet their jaws held dozens of replacements ready to emerge. In Nigersaurus, for example, new teeth could appear roughly every 2 weeks, a record among known dinosaurs. This rapid turnover allowed it to eat continuously without losing efficiency. The discovery of tooth regeneration in dinosaurs also helps scientists understand the transition from reptiles to birds. Early birds, descended from theropod dinosaurs, gradually lost the ability to regrow teeth as their diets and lifestyles changed. Instead of toothy jaws, they developed beaks, lighter, more versatile tools for handling food. Yet the genetic remnants of tooth-making still exist in modern birds, hidden in their DNA like faint echoes of a prehistoric past. To imagine a dinosaur's mouth was to imagine a living factory, teeth breaking, falling, and renewing in an endless rhythm. It was a system of renewal that reflected the broader resilience of life itself. Even as they faced constant wear and danger, dinosaurs were built to adapt, to endure, and to keep going. Each tooth that fell was not a loss but a promise of replacement, a symbol of nature's astonishing ability to sustain itself through cycles of destruction and renewal. In the end, the ability of dinosaurs to regenerate teeth is more than a biological curiosity. It is a window into their vitality. It reminds us that these ancient creatures were not static monsters of stone, but living, dynamic beings, continuously repairing and renewing themselves. Their smiles, if they could be called that, were not fixed in time but ever-changing, living proof that in the age of dinosaurs, even something as small as a tooth was part of the grand machinery of survival. It is astonishing to think that the small, bright creatures that flit across the morning sky are the descendants of the great reptiles that once ruled the earth. Every bird alive today, from the humblest sparrow to the soaring eagle, is, in truth, a living dinosaur. This is not a metaphor or a poetic idea, but a scientific reality, one uncovered through decades of fossil discoveries and the meticulous study of evolution. The line that connects birds to dinosaurs is not broken or faint. It is direct, clear, and continuous, stretching back more than 150 million years to a time when feathered creatures shared the world with colossal giants. In the late Jurassic period, the forests of what is now Europe and Asia were home to a remarkable animal known as Archaeopteryx. With its feathered wings, sharp claws, and long, bony tail, it embodied the bridge between two worlds, the ancient world of reptiles and the emerging one of birds. Archaeopteryx could glide, perhaps even flutter short distances, but it still bore the unmistakable traits of its dinosaurian ancestors. Its discovery in the 19th century transformed science's understanding of evolution, showing that the boundary between birds and dinosaurs was not as rigid as once believed. Over time, countless fossils confirmed that feathers did not suddenly appear with birds. They first evolved among small, predatory dinosaurs, possibly for insulation or display, long before they became tools for flight. The connection becomes even clearer when one looks closely at modern birds. Beneath their feathers, their skeletons tell a prehistoric story. The wishbone, or furcula, that strengthens a bird's chest during flight is the same structure found in many theropod dinosaurs. The group that includes fearsome hunters like Velociraptor and Tyrannosaurus rex. Their feet, too, are almost identical in design, with 3 forward-pointing toes and 1 angled backward for perching. Even the air sacs that fill a bird's body and help it breathe efficiently while flying have ancient origins. They were present in the lungs of dinosaurs, lightening their bones and improving oxygen flow. Every flap, chirp, and wing beat is a whisper from that ancient past. Feathers, one of the most defining features of birds, were not originally meant for flight at all. Early feathered dinosaurs used them for warmth or to show off colors during courtship, much like modern peacocks. Only later did evolution refine feathers into aerodynamic tools. The transformation from ground-dwelling predator to airborne traveler was gradual, guided by millions of years of adaptation. Some dinosaurs began leaping, gliding, and eventually mastering powered flight, opening a new dimension of existence that no land animal had ever fully conquered before. In doing so, they escaped many of the environmental traps that confined their earthbound relatives. When the age of dinosaurs ended about 66 million years ago, most species perished in the global catastrophe caused by a massive asteroid impact. Yet not all dinosaurs vanished. The small, feathered ones, the ancestors of modern birds, managed to survive, perhaps because their size, diet, and ability to fly gave them an advantage in a devastated world. From those survivors, life began anew. They spread across continents, diversified, and filled the skies with movement and sound. In their survival, the dinosaur lineage did not die, it merely transformed. To see a bird today is to glimpse deep time in motion. The robin hopping across a garden, the gull riding the wind over the sea, the hawk spiraling high above the fields. All carry within them the legacy of creatures that once shook the earth beneath their feet. The connection is humbling and beautiful. Life, ever adaptable, reshaping itself across epochs, finding new ways to endure. The dinosaurs are not gone. They are alive, watching from the branches and flying overhead, their ancient eyes now bright with the light of morning. Supersaurus was one of the longest creatures ever to walk the earth, a true giant among giants in the age of dinosaurs. Stretching more than 30 meters from head to tail, longer than 3 city buses end to end. It embodied the grandeur and mystery of the Mesozoic world. Its name, meaning super lizard, feels almost inadequate when one considers the scale of its body, the enormity of its neck, and the sweep of its tail, which could have lashed the air like a whip. This immense creature lived around 150 million years ago, during the late Jurassic period, when the world was lush, humid, and teeming with life. In that vast, green world, Supersaurus moved like a slow-moving continent of flesh and bone, a living monument to nature's power to create on an epic scale. To imagine Supersaurus is to picture an animal so immense that it redefined what it meant to be large. Its neck alone could reach over 15 meters in length, allowing it to browse from the tops of ancient conifer trees that few other herbivores could touch. His body, though massive, was built with surprising efficiency. Hollow spaces in its bones made it lighter than one might expect, an adaptation that allowed it to support its immense size without collapsing under its own weight. Its long tail balanced that extraordinary neck, and its pillar-like legs supported it with quiet strength as it wandered through the fern-filled plains of prehistoric North America. The world Supersaurus inhabited was shared with other enormous sauropods, Diplodocus, Apatosaurus, and Brachiosaurus, each one an evolutionary marvel, adapted to reach food sources others could not. Yet Supersaurus stood out even among these titans. It was one of the longest animals ever known, its length rivaling or even exceeding that of the blue whale, the largest creature alive today. Though not the heaviest of the sauropods, it possessed a grace that came from its slender build and elongated form. It was less bulky than its relatives, but its stretched proportions made it seem almost endless, as if its body could bridge the distance between trees and horizon. For much of the 20th century, Supersaurus was known only from a few scattered bones, an enormous shoulder blade here, a vertebra there. From those fragments, paleontologists began to piece together its identity, slowly realizing that these fossils belonged not to a familiar species, but to one of unprecedented size. Each discovery expanded the picture of this magnificent creature, revealing a skeleton that dwarfed nearly every other land animal in history. In the dry rock beds of Colorado, where its remains were first found, its fossilized bones became silent witnesses to a time when life reached its grandest expressions. Despite its size, Supersaurus was a gentle giant. It fed on plants, stripping branches with its peg-like teeth and swallowing vegetation by the mouthful. It likely traveled in herds, moving slowly across the Jurassic floodplains in search of fresh growth. Its enormous body required vast amounts of food, and it probably spent much of its life eating, just to sustain the energy needed to move its colossal frame. Yet, for all its size, it was not invulnerable. The world it lived in was full of predators like Allosaurus, who may have dared to attack the young or the weak, testing the edges of what even a giant could withstand. To think of Supersaurus today is to be reminded of the scale of life's imagination. In a world where most creatures are measured in meters, it stretched into tens of them. In a time when the Earth's continents were still drifting apart, it walked across the young landscapes of North America like a living bridge between sky and ground. Its existence tells a story of evolution's boundless creativity, of nature's ability to build life on a scale that defies comprehension. Though its bones now lie silent in stone, the image of Supersaurus endures, a reminder that once, long ago, the Earth itself seemed to breathe through the movements of giants. Microraptor was one of the smallest dinosaurs ever discovered, a creature so delicate and finely built that it might have perched on a human arm like a bird. It lived around 120 million years ago, during the early Cretaceous period, in the forests of what is now northeastern China, a world of towering conifers, ferns, and quiet lakes. While enormous predators and lumbering herbivores roamed other parts of the Earth, Microraptor ruled a different kind of kingdom, the treetops. Barely the size of a crow, it was a predator of the air and branches, perfectly adapted to a life of agility and precision. At first glance, Microraptor's fossilized remains are almost ghostly, fine bones surrounded by the impressions of feathers so well preserved that their patterns can still be traced in stone. Its body was covered in sleek plumage, not just along its arms but on its legs as well. These feathers formed 4 distinct wings, giving it a shape unlike any other dinosaur. With a pair of wings on its forelimbs and another pair on its hind limbs, Microraptor could glide through the forest like a living kite, catching air currents as it moved from tree to tree. This strange design, both primitive and elegant, represents one of nature's earliest experiments with flight. Microraptor's feathers were more than just tools for gliding. They were likely beautiful. Chemical traces preserved in fossils suggest that its plumage shimmered with iridescent hues, dark and glossy like the feathers of a raven. This sheen may have played a role in display or camouflage, helping it blend with the shadows of the forest canopy. Its small, curved claws and long tail, also feathered, gave it remarkable control as it maneuvered through the air. When it landed, it could scurry along branches with the quickness of a squirrel, always alert for the flicker of movement that meant prey. Despite its size, Microraptor was a capable hunter. Its sharp teeth and grasping claws were perfectly suited to catching small animals such as lizards, mammals, and even other birds. Fossils have preserved the remains of its last meals. Tiny bones from a bird, fish scales, and the skeleton of a small mammal, all swallowed whole. These discoveries show that it was both opportunistic and skilled, able to hunt in trees or swoop down over water to snatch its prey. In this way, Microraptor occupied a unique ecological niche, bridging the worlds of ground and sky. Its smallness was not a weakness but an advantage. Large dinosaurs could not move easily through dense forests or leap between trees, but Microraptor could glide silently, evade predators, and exploit food sources unreachable to others. Its world was one of motion and precision rather than brute strength. Every jump, every glide was a calculation, a delicate balance of air, muscle, and instinct. In its light body and 4-winged form, one can see evolution's experimentation, a step on the path that would eventually lead to the true flight of modern birds. Microraptor's discovery changed how scientists understood the evolution of flight. For years, the debate raged over whether birds evolved flight from ground-dwelling runners or from tree-dwelling gliders. Microraptor provided powerful evidence for the latter. A small dinosaur already equipped for life among branches, using its limbs and feathers to soar. It was proof that the boundary between dinosaur and bird was not abrupt but gradual, a continuum of change and adaptation stretching across millions of years. To imagine Microraptor is to imagine grace made small. Its world was filled with the whisper of feathers and the flicker of movement through the green canopy. It was a creature of balance and elegance, as fragile as it was fierce. Though it vanished long ago, its legacy endures in every bird that takes flight today. Microraptor reminds us that even the smallest of creatures can leave the most profound marks on the story of life, carrying the dream of flight long before wings ruled the sky. Dinosaur eggs were as diverse and fascinating as the creatures that laid them. Far from being uniform in shape or texture, these ancient eggs came in a remarkable variety of sizes, patterns, and structures. Some were as small as a sparrow's egg, while others were larger than a human head. Their shells ranged from thin and leathery to thick and hard, with surfaces that could be smooth, rough, or covered in tiny pores and ridges. Each variation reflected the unique biology and nesting behavior of the dinosaurs themselves, offering scientists rare glimpses into the earliest moments of life in a prehistoric world. When the first dinosaur eggs were discovered in the 19th century, they were often mistaken for stones or fossils of plants. It was only after more discoveries, especially in Asia and South America, that paleontologists began to understand what they were looking at. These eggs revealed that dinosaurs, much like modern reptiles and birds, reproduced by laying clutches of eggs in carefully chosen places. But the similarities ended there. As researchers uncovered more fossil nests, they realized that dinosaur eggs were incredibly diverse, shaped by the size, environment, and evolutionary lineage of the species that produced them. In terms of size, the range was astonishing. The smallest known dinosaur eggs, belonging to small theropods, measured only a few centimeters long, tiny enough to fit in the palm of a hand. On the other extreme were the eggs of giant sauropods such as Hypsilosaurus, which could reach up to 40 centimeters in diameter and weigh several kilograms. Yet even these massive animals didn't lay eggs as enormous as one might expect. Their sheer body size limited how large an egg could be before the shell would collapse under its own weight. Instead, sauropods likely laid many medium-sized eggs at once, increasing the chances that at least some would survive. The texture of dinosaur eggshells varied just as much as their size. Some species laid eggs with hard, calcified shells, similar to those of birds, providing strong protection for the embryo inside. Others, especially early dinosaurs, produced leathery, flexible eggs more like those of modern reptiles. The difference likely depended on nesting habits and environmental conditions. In humid or buried nests, a softer shell would allow gas exchange and moisture absorption, helping the embryo develop. In drier environments, harder shells prevented desiccation and offered defense against trampling or predators. Even the microscopic structure of the shells tells a story. Some were made up of multiple layers of crystallized calcium carbonate, while others had complex networks of pores that regulated the flow of air to the developing young. The discovery of fossilized dinosaur nests adds even more depth to this story. Some species arranged their eggs in neat circular patterns, suggesting deliberate care in placement, perhaps to ensure even incubation. Others buried their eggs under vegetation or soil, using the natural heat of decay or the sun's warmth to hatch them. The famous nesting sites of Myasora in Montana revealed something extraordinary. Evidence that these dinosaurs tended their nests, bringing food to their hatchlings and protecting them, a level of parental care that mirrors the behavior of modern birds. Eggshell fossils have even preserved delicate surface details, such as ridges and nodules, that may have helped camouflage the eggs or strengthen them against external pressure. In some cases, pigment traces have been found, hints of ancient coloration that could have served as camouflage from predators or perhaps even as a means of visual communication between parents and eggs, as seen in some bird species today. Each fossilized egg is a time capsule, preserving a moment that occurred millions of years ago, the quiet beginning of life in a world dominated by giants. They remind us that dinosaurs were not just massive and fearsome, but also tender in their own ways. Creatures that laid eggs with care and left behind signs of complex reproductive strategies. Through these fragile shells, scientists glimpse the continuity of life's patterns, how birth, protection, and survival connect across eras. From leathery ovals buried in sand to hard-shelled spheres guarded in nests, dinosaur eggs capture the beauty of diversity that evolution shaped across countless generations. They speak of a time when every species, no matter how large or small, began as something delicate and full of potential, an embryo waiting inside a shell, ready to join the living world under the vast skies of the Mesozoic Earth. Dinosaurs were not confined to one corner of the Earth. They were global creatures, inhabiting every continent, from the steaming jungles near the equator to the icy reaches of what would one day become the poles. Their fossils have been found in deserts, mountains, swamps, and plains, buried beneath the shifting crust of the planet they once ruled. During the long span of their reign, over 165 million years, the continents themselves were in motion, splitting and drifting apart, yet dinosaurs adapted to each change, spreading across the face of the Earth as if the planet were their shared, endless home. In the beginning, when dinosaurs first appeared in the late Triassic period, the world's landmasses were united in a single supercontinent called Pangaea. It was a vast and varied landscape, stretching from pole to pole, where deserts met forests and volcanoes shaped the horizon. In this connected world, dinosaurs could roam freely, their early forms spreading rapidly across the continents. They evolved into countless species, each suited to the environments they encountered, some growing large to graze on the abundant vegetation, others staying small and swift to hunt or hide. Their footprints crossed what would one day become South America, Africa, and Europe, long before oceans divided them. As millions of years passed, Pangaea began to break apart. The continents drifted slowly into the shapes we recognize today, and with that movement came new climates and challenges. But the dinosaurs adapted again. On the newly formed landmasses, they evolved in isolation, developing unique forms that reflected their surroundings. In what is now North America, vast herds of hadrosaurs and horned dinosaurs roamed the fertile plains. In South America, titanic sauropods like Argentinosaurus grew to almost unimaginable sizes, towering over forests of ferns and conifers. Across the seas, in what would become Asia, nimble raptors evolved, their intelligence and agility setting them apart. Each continent became a laboratory of evolution, yet all were united by the presence of dinosaurs. Even in the cold, dark regions near the poles, dinosaurs thrived. Fossil evidence from Antarctica and Alaska reveals that these creatures endured long winters and months of darkness, adapting to climates far harsher than the tropical heat usually associated with their kind. Some scientists believe they migrated with the seasons, moving in herds to follow the sun, while others may have stayed year-round, developing strategies to cope with freezing temperatures and limited food. Their presence in such extreme environments proves their resilience and adaptability. They were not merely survivors of one world, but masters of many. The global reach of dinosaurs also tells the story of life's ability to adapt to change. They evolved in an age of shifting continents, rising mountains, and fluctuating seas, and they flourished through it all. Where volcanoes erupted, forests grew again. Where oceans expanded, new lands formed. And wherever there was land to walk on, dinosaurs found a way to live. Their fossils are now embedded in stone from Patagonia to Mongolia, from the Utah deserts to the Australian outback, silent witnesses to a time when their kind dominated every ecosystem on Earth. To say that dinosaurs were global is to recognize the unity of life across deep time. They were the first true citizens of the planet, creatures whose existence spanned continents and climates, whose diversity reflected the vast possibilities of evolution. Today, the discovery of their bones in far-flung places reminds us how connected the world once was, and still is. Each fossil, unearthed from a different corner of the Earth, is a piece of the same story. A story of endurance, expansion, and adaptation. The dinosaurs' dominion was not limited by boundaries or oceans. They belonged to the whole Earth, and for millions of years, the Earth belonged to them. Many dinosaurs had bones that were hollow inside, a feature that gave them a surprising blend of strength and lightness. To the casual observer, such bones might seem fragile, as if a creature built from them would crumble under its own weight. Yet hollow bones are anything but weak. Nature perfected this design long before humans discovered the power of lightweight engineering. In dinosaurs, these air-filled structures became an essential adaptation, one that shaped how they moved, breathed, and eventually gave rise to the birds that soar above us today. When paleontologists examine the fossilized bones of certain dinosaurs, they often find thin outer walls enclosing intricate networks of air spaces. These bones are described as pneumatic, meaning filled with air. The air cavities were connected to the respiratory system, large sacs of air that extended beyond the lungs and flowed through parts of the skeleton. This arrangement was especially common in theropods, the two-legged carnivores like Tyrannosaurus rex and Velociraptor, and in the enormous long-necked sauropods. The bones, though hollow, were reinforced by internal struts and ridges, creating a structure that could withstand tremendous forces without unnecessary heaviness. For predators, hollow bones were a secret advantage. Hunting required agility, speed, and balance, qualities hard to achieve if one skeleton was too dense. By shedding excess weight without sacrificing power, theropods could move swiftly and strike with precision. Their light frames allowed them to chase prey, leap, and twist their bodies efficiently. Even the mighty T-Rex, which could weigh several tons, benefited from bones that reduced the total mass of its body. Its hollow skull, for instance, was large enough to hold powerful jaw muscles and yet light enough to be supported by the neck without collapse. In the towering sauropods, hollow bones served a different but equally vital purpose. These creatures reached astonishing sizes, with necks stretching as long as a city bus. Solid bones would have made such proportions impossible. Their skeletons would have been too heavy to lift or support. But with hollow vertebrae, filled with air sacs, the sauropods could maintain their enormous forms while keeping their skeletons manageable. The design also worked hand in hand with their breathing system. Air sacs connected to their lungs may have extended through their necks and bodies, ensuring that oxygen flowed efficiently through their vast bulk. In this way, hollow bones were part of a sophisticated respiratory network far more advanced than that of any modern reptile. This system closely resembles that of today's birds, which also possess pneumatic bones. The connection is no coincidence. Birds are the living descendants of theropod dinosaurs, and their hollow skeletons are a direct inheritance from those ancient ancestors. The same principle that once allowed Velociraptor to sprint across prehistoric plains now allows an eagle to glide effortlessly through the sky. What began as an adaptation for agility and efficient breathing eventually became one of the defining traits of flight. To understand how revolutionary this was, one need only imagine the Earth's surface in the age of dinosaurs. Vast, hot, and filled with danger. Every ounce of saved weight mattered. Hollow bones meant less energy spent on movement, quicker escapes, and more efficient hunting. They were an evolutionary experiment in lightness that proved astonishingly successful. Even the most fearsome predators carried within their bodies a delicate architecture of air and bone, a balance between fragility and endurance. Yet the true marvel lies in how this adaptation transformed over time. What began as a way to move and breathe more effectively on land evolved into the framework for flight. The same hollow bones that supported dinosaurs on the ground eventually lifted their descendants into the air, turning running limbs into wings and heavy bodies into graceful flyers. In those empty spaces within the bone lay the promise of the sky itself. So when we look at the skeleton of a bird today, we are seeing more than a modern design. We are seeing the echo of a prehistoric innovation. The hollow bones that once filled the lungs of giants and hunters continue to serve life millions of years later, a testament to evolution's genius. They remind us that lightness does not mean weakness, and that even within something as solid as bone, there can be air, efficiency, and the breath of ancient life that still lingers in the world today. Many dinosaurs did not live solitary lives but moved together in vast herds, their footsteps rumbling across the ancient landscapes like distant thunder. They traveled as families, as communities, bound by instinct and survival. This herding behavior, revealed through fossil evidence scattered across the globe, shows that dinosaurs were not merely creatures of strength and size, but of cooperation and connection. The earth they inhabited was immense and sometimes harsh, and in unity they found protection, warmth, and a rhythm that pulsed through every migration and every season. Fossilized trackways, rows of footprints preserved in ancient mud, speak most clearly of their herds. In these stone records, paleontologists have found paths of dozens, even hundreds of individuals moving together in the same direction, their prints overlapping in careful alignment. The spacing between steps shows not chaos but coordination, a sign that they walked in groups rather than as wandering loners. These traces, frozen in time, offer a window into their social lives. They show adult dinosaurs walking alongside juveniles, their smaller footprints nestled among the larger ones, suggesting that the young were protected within the moving group. The herd was both a shield and a school, a place where survival was learned and shared. Among the great herbivores, herding was likely a way of life. Sauropods such as Apatosaurus and Diplodocus, with their enormous bodies and long necks, may have formed immense, slow-moving groups that roamed the floodplains in search of vegetation. To see such a herd would have been an awe-inspiring sight. Dozens of towering animals stretching across the horizon, their necks swaying gently as they fed from the treetops. Moving together, they could strip vast areas of greenery before moving on to fresh pastures, leaving behind the marks of their passage in trampled ferns and churned mud. For the young sauropods, the center of the herd offered safety from predators. Hidden within the living fortress of their elders' legs and tails. Other dinosaurs, too, found strength in numbers. The hadrosaurs, often called duck-billed dinosaurs, are among the best examples of true herd behavior. Fossil beds filled with the bones of hundreds of individuals suggest that they lived, migrated, and perhaps even died together. These herds likely crossed rivers and plains in search of seasonal feeding grounds, their calls echoing through the air as they communicated through sound and gesture. The complexity of their crests, structures that may have amplified voices or signaled visually, hints at a rich social life built on communication. They may have warned one another of danger, guided their young, or reinforced bonds through calls that rolled like music across the prehistoric plains. Predators, too, sometimes hunted in groups, taking advantage of the herds that sustained them. Packs of smaller theropods may have coordinated attacks, singling out weak or young prey from the masses. Even the mighty Tyrannosaurus might have tolerated others of its kind, forming temporary associations that allowed them to dominate a region. The balance between herds of herbivores and the predators that followed them created a dynamic, interwoven ecosystem, each shaping the other's behavior and evolution. Herding required more than instinct, it reflected intelligence and awareness. To move together, to protect the young, to communicate across distances. All of this suggests a level of social structure once thought impossible in reptiles. These herds were not mindless mobs. They were organized, responsive, and alive with collective purpose. Within them, individuals depended on one another, their lives intertwined by the shared need to survive. To imagine these herds today is to see the ancient world not as a place of isolated giants, but as one of movement and connection. Across the open plains and forests of the Jurassic and Cretaceous, the ground trembled beneath their passing. Dust rose, leaves swayed, and the air filled with the sound of life moving as one. Long before mammals or humans formed societies, the dinosaurs had already discovered the strength of the group, the ancient truth that together, life endures. For most of history, dinosaurs were imagined in shades of mystery, gray, green, or brown creatures painted by guesswork and imagination. Their colors were thought to have vanished forever, lost with their skin and feathers to the passage of millions of years. But in recent decades, science has achieved something extraordinary. Paleontologists have discovered ways to estimate what colors some dinosaurs may have worn, peeling back the veil of deep time to reveal patterns, pigments, and shades that once shimmered across ancient skin and feathers. Through the delicate study of fossilized remains, these scientists have begun to see dinosaurs not as drab monsters of stone, but as vibrant, living animals full of color and complexity. The key to this revelation lies in microscopic structures called melanosomes. Tiny, pigment-bearing organelles found inside cells. In modern animals, different shapes of melanosomes are linked to different colors. Rod-shaped ones usually produce black or gray tones, while rounder ones create reddish or brown hues. When feathers or skin are fossilized under the right conditions, these melanosomes can sometimes remain preserved, embedded in the ancient tissue. By examining their size, shape, and arrangement with powerful electron microscopes, paleontologists can make educated guesses about what colors they once produced. One of the first and most famous examples came from a small feathered dinosaur called Anchiornis, discovered in China. Its fossils were so exquisitely preserved that scientists could map the melanosomes across its feathers. The result was astonishing. A pattern of black and white feathers with a striking reddish crest, much like a modern woodpecker or jay. Suddenly, the past wasn't gray anymore. It was alive with contrast and character. Since then, similar studies have revealed color hints in other dinosaurs and ancient birds, from glossy black plumage to possible iridescent sheens that shimmered in the sunlight. This discovery reshaped how we imagine the dinosaur world. Once depicted as reptilian beasts of dull camouflage, many dinosaurs may have looked more like tropical birds, dazzling their surroundings with vivid hues. Some likely used color for display, signaling health, strength, or readiness to mate. Others might have relied on earth tones to blend into their environments, hiding from predators or stalking prey unnoticed. For young dinosaurs, bright patterns could have warned others of toxicity or served as signals within herds. Color was not just decoration, it was communication, survival, and identity. Yet these reconstructions come with limits. Only a fraction of dinosaur fossils preserve soft tissues, and even when melanosomes are present, they represent just part of the color story. Structural colors, those created by the microscopic arrangement of surfaces that reflect light to produce blues, greens, or iridescence, are much harder to detect in fossils. Chemical traces of other pigments, like carotenoids and porphyrins, rarely survive over millions of years. As a result, while paleontologists can often estimate basic hues, the full richness of a dinosaur's coloration may remain partly hidden, shimmering just beyond our reach. Still, each new discovery brings us closer. With advanced imaging and molecular techniques, scientists are learning to read fossils like ancient canvases. Even patterns like stripes, spots, or patches can sometimes be inferred from the distribution of melanosomes or the texture of fossilized skin. These breakthroughs transform paleontology into a kind of detective art, where evidence and imagination blend to recreate the visual world of creatures long gone. The implications reach beyond mere aesthetics. Understanding dinosaur coloration helps scientists explore behavior, ecology, and evolution. It can reveal how dinosaurs interacted with their surroundings, how they used camouflage or display, and how their appearance influenced the rise of birds. Color connects the ancient past to the living present, bridging the gap between fossil and feather. To imagine a dinosaur now is to imagine not a dull shadow of the past, but a being of brilliance, perhaps with a crimson crest glinting in the dawn, or dark, glossy feathers gleaming under prehistoric sun. Through the fragile traces of pigment preserved in stone, We are rediscovering a lost world in color, one that once pulsed with beauty, danger, and life. The fossils, once silent, now whisper their hues again, painting the Mesozoic in shades we can finally begin to see. Among the many strange and fascinating habits of dinosaurs, one of the most surprising is that some of them swallowed stones on purpose. These stones, called gastroliths, meaning stomach stones, were not a sign of odd appetite or confusion, but an ingenious adaptation. Hidden within the bellies of plant-eating dinosaurs, the smooth, rounded rocks served as natural tools to grind tough vegetation that their teeth alone could not handle. This curious behavior, shared by certain modern birds and reptiles, reveals yet another layer of intelligence and survival strategy in the ancient giants that once ruled the earth. The world of the herbivorous dinosaur was not an easy one. Many of them lived on a diet of fibrous ferns, cycads, and conifer needles, plants that were rough, coarse, and difficult to digest. Unlike mammals, most dinosaurs did not have the benefit of complex chewing teeth capable of breaking down food thoroughly before swallowing. Instead, they tore or snipped at plants and gulped them down in large chunks. To make up for this, some species developed a remarkable solution. They swallowed stones that would take up residence in their stomachs, helping to mash and grind the plant material as it moved through the digestive system. Evidence of this behavior comes from fossil sites where polished, rounded stones have been discovered among dinosaur skeletons. These stones are often too smooth and too out of place to have arrived there by chance. In species like Seismosaurus, Diplodocus, and Psittacosaurus, scientists have found clusters of gastroliths near where the stomach would have been. When examined, the stones bear the telltale were marks of long use, scratched, rounded, and smoothed by the rhythmic motion of grinding against food and one another inside a dinosaur's body. For massive sauropods, whose long necks reached treetops and whose bellies could hold hundreds of liters of plant matter, such stones would have been essential. Their teeth were peg-like and simple, more suited for stripping leaves than for crushing them. Once swallowed, the leaves would mix with stones inside a muscular organ similar to the gizzard of modern birds. There, constant churning turned the stones into internal millstones, breaking down the fibrous matter so that the nutrients could be absorbed more efficiently. Without this system, the giant plant eaters might have struggled to sustain their enormous bodies. Interestingly, not all dinosaurs relied on this strategy. Some had evolved more advanced teeth, capable of chewing plants directly in their mouths. Duck-billed hadrosaurs, for instance, had hundreds of tightly packed teeth forming complex, grinding surfaces that made gastroliths unnecessary. But for those species without such dental sophistication, the stomach stones provided an elegant alternative, an example of nature's resourcefulness in adapting to different challenges. The idea of swallowing stones may sound uncomfortable, but it is far from unique to dinosaurs. Today, birds such as chickens, ostriches, and pigeons still use gastroliths for the very same reason. Crocodiles and seals have also been known to swallow stones, sometimes to help with digestion, other times to aid balance in the water. The behavior is an ancient one, stretching across millions of years, showing how some biological strategies endure through time with only minor changes. What makes the dinosaur use of gastroliths so fascinating is the glimpse it gives into their daily lives. It suggests that they were not clumsy or mindless creatures but animals capable of instinctive problem-solving. They interacted with their environment in complex ways, choosing and swallowing the right kinds of stones, often selecting quartz or granite for their hardness and durability. Over time, they might replace worn stones with fresh ones, maintaining the efficiency of their internal grinding system, much like replacing tools in a workshop. When one imagines these stones at work inside a living dinosaur, tumbling and turning as the creature moved through forests or plains, it adds a dynamic layer to our understanding of prehistoric life. The stones themselves, silent and heavy, became part of the living machinery of giants, helping to sustain the endless cycles of eating, digesting, and surviving. Long after the dinosaurs vanished, their gastroliths remained, polished by time and still bearing the marks of ancient digestion. Some now rest in museum displays, unassuming pebbles that once helped feed titans. In their smooth surfaces lies a quiet story of adaptation, the story of how even the mightiest animals once depended on something as humble as a handful of stones to thrive in a wild and unforgiving world. Some dinosaurs were not only large or swift, they were armored, clad in natural defenses that turned their bodies into living fortresses. These creatures, covered in plates, spikes, and bony shields, were the tanks of the prehistoric world, built to withstand the claws and teeth of predators that prowled their ancient landscapes. Their armor came in many forms and evolved independently across different groups, a testament to how dangerous their world was and how inventive nature could be in the art of protection. To survive in an age of giants, some dinosaurs became fortresses of bone and horn, turning vulnerability into resilience. Among the most famous of these armored dinosaurs were the ankylosaurs, low-slung herbivores whose entire bodies were encased in thick plates of bone called osteoderms. Embedded in their skin like natural chainmail, these bony plates created a mosaic of defense that could deflect bites and blows. Along their backs, rows of spikes and ridges added further protection, while their tails ended in massive clubs of solid bone, deadly weapons that could crush the legs of any predator foolish enough to attack. An adult ankylosaur must have been an imposing sight, its wide, armored body glinting in the sunlight, moving slowly but purposefully across the Cretaceous plains. When threatened, it did not run. It stood its ground, swinging its tail with devastating force. In the silent duel between offense and defense, the ankylosaurs were living proof that survival did not always belong to the swift. The stegosaurs, who lived millions of years earlier, wore a different kind of armor. Their bodies were lined with large, flat plates rising from their backs in twin rows, creating a silhouette unlike any other creature on Earth. These plates may have served several purposes: protection, display, and even temperature regulation, as blood vessels ran through their surfaces. At the end of the tail, for sharp spikes, known as the thagomizer, formed a formidable weapon. A stegosaurus, with its head low and tail ready to strike, was far from defenseless. Fossil evidence of healed wounds on carnivorous dinosaurs suggests that these spikes were not just for show. They could pierce deep and leave lasting damage. In a world filled with predators like Allosaurus, Such weapons could mean the difference between life and death. Armor was not limited to these iconic species. Some smaller dinosaurs, such as the nodosaurs, wore similar protective coverings but lacked the tail club of their ankylosaur cousins. Their armor was heavier on the shoulders and back, sometimes adorned with long, blade-like spikes that discouraged attack. Even among the larger plant eaters, certain sauropods evolved partial armor. Bony plates scattered along their backs and necks, perhaps to defend against predators that grew ever more cunning and strong. The variety of armor across the dinosaur lineage speaks to evolution's endless creativity, adapting form and function to fit the demands of survival. Yet armor came with trade-offs. It made movement slower, bodies heavier, and energy demands greater. These dinosaurs had to balance defense with the need to feed and move efficiently. Their bulk alone was often enough to deter attackers, but their armor turned that bulk into something far more intimidating, a statement that they were not prey to be taken lightly. Over millions of years, these defenses shaped not only their survival but also the behavior of the predators that hunted them. To bring down an armored dinosaur required speed, strategy, and often teamwork. In this way, the evolution of armor drove an evolutionary arms race, pushing both predator and prey to new heights of adaptation. To imagine these armored dinosaurs today is to picture a landscape alive with contrasts. Graceful, feathered hunters stalking through shadows while heavy, plated herbivores lumbered beneath the open sky. The glint of sunlight on a row of bony plates, the thunder of steps across dry earth, the slow swing of a tail club ready to strike. All were part of the rhythm of life in that ancient world. Their armor was more than protection. It was identity, strength made visible. And in their fossilized remains, that armor still endures, a lasting testament to creatures who turned their bodies into shields against time itself. Long before birds filled the skies, feathers already adorned the bodies of dinosaurs. For centuries, dinosaurs were imagined as scaly, reptilian creatures, their skin rough and bare like that of lizards or crocodiles. Yet as fossils continued to emerge from the rocks of China, Mongolia, and beyond, a new image began to form, one that shimmered with texture, color, and life. Some dinosaurs, it turned out, were covered in feathers. Not just primitive filaments, but downy coats, quills, and even flight-ready plumes. The discovery transformed our understanding of what dinosaurs were and how they lived, revealing that their world was far more dynamic and vibrant than once believed. The first hints came from small theropods, the group of dinosaurs that included swift predators like Velociraptor and the ancestors of birds. Fossils preserved in fine volcanic ash showed impressions of soft, hair-like structures radiating from their skin. At first, scientists thought these might be simple fibers, but further discoveries revealed unmistakable feathers, branched, delicate, and patterned just like those of modern birds. These feathers did not appear suddenly. They evolved in stages. Some species had only wispy filaments for insulation, while others developed complex feathers suited for display or flight. This gradual transformation tells a story of evolution experimenting over millions of years, refining form and function until feathers became one of nature's most remarkable inventions. Feathers served many purposes long before flight. For small dinosaurs, they provided warmth, trapping heat and allowing them to survive in cooler climates. Others used feathers as tools of communication and attraction. Fossils suggest that some species had fans, crests, or frills of feathers, perhaps colored in bright hues to signal strength or readiness to mate. The ability to display color and pattern would have transformed their behavior, adding layers of social interaction and beauty to their world. Just as peacocks today spread their tails in dazzling display, ancient dinosaurs might have done the same, their plumage shimmering under the Mesozoic sun. The connection between dinosaurs and modern birds becomes especially clear when examining creatures like Archaeopteryx, discovered in the limestone quarries of Germany. It had wings with fully formed feathers, yet it also bore teeth, claws, and a long bony tail, features unmistakably dinosaurian. Archaeopteryx stands at the crossroads of evolution, part reptile and part bird, showing that flight did not begin in a single leap but through countless small adaptations. Other species, such as Microraptor, took the concept further, with feathers not only on its arms but on its legs as well, forming 4 wings that allowed it to glide between trees. These discoveries blur the line between bird and dinosaur so thoroughly that, in truth, the line hardly exists at all. Feathers also reveal a deeper story about dinosaur physiology. To sustain feathers and later powered flight, these animals needed high metabolism and active lifestyles. They were not sluggish, cold-blooded reptiles, but energetic, warm-blooded creatures capable of rapid movement and complex behavior. Feathers, then, were not just decoration, they were evidence of vitality. They mark a turning point in the history of life, when dinosaurs began to break the boundaries of the land and reach toward the sky. Today, when we look at birds, we are seeing the living descendants of those feathered dinosaurs. Every fluttering sparrow, every eagle in flight, carries within it the ancient blueprint of its Mesozoic ancestors. The feathers that once kept a small predator warm or signaled to a mate now fill the air with song and motion. They are a link across time, a reminder that the age of dinosaurs never truly ended. It simply took wing. The discovery that some dinosaurs had feathers reshaped not only science but imagination, turning creatures once thought monstrous into beings of grace, color, and endless possibility. Through their feathers, they remain alive in every heartbeat that stirs the air. In the vast prehistoric world, daylight did not belong to all creatures equally. While many dinosaurs thrived under the blazing sun, others waited for dusk to fall, their time beginning as shadows lengthened across the primeval landscape. These were the night hunters, dinosaurs that prowled under starlight, guided not by sight alone but by finely tuned senses evolved for survival in darkness. Their story, pieced together from bones, skulls, and delicate structures within fossilized eyes, reveals that the age of dinosaurs was as alive at night as it was by day. For a long time, scientists imagined the Mesozoic world as one ruled by diurnal giants, where sunlight illuminated the activities of herbivores grazing and predators chasing. But closer examination of fossil evidence, particularly the shape and structure of eye sockets, began to suggest otherwise. The size of the eye and the proportion of its inner ring, called the sclerotic ring, can indicate whether an animal was adapted for daylight, twilight, or nighttime vision. Species with large eyes and wide openings in these rings likely saw well in dim light, just as modern owls and cats do. In several dinosaur fossils, especially among small and agile predators, these features are strikingly prominent. Theropods such as Trudon, a small but intelligent predator, provides some of the clearest clues. Its eyes were enormous relative to its skull, suggesting exceptional night vision. Its brain case shows large regions devoted to visual processing, hinting at an animal capable of navigating and hunting in near darkness. This adaptation would have allowed Trudon to stalk prey while larger, day-active predators rested, giving it an edge in survival. Its slender limbs and quick reflexes further suggest it relied on stealth and agility rather than brute strength, a perfect formula for a nocturnal hunter. Other dinosaurs, such as Velociraptor, may have also used the cover of night to their advantage. Though not strictly nocturnal, they likely hunted during the cooler hours of dawn and dusk, when their prey, small mammals, reptiles, and perhaps young dinosaurs, were active but visibility was low. This behavior, known as crepuscular hunting, reduced competition with other predators and allowed them to exploit different ecological niches. The desert-like environments many of these raptors inhabited would have been unbearably hot during the day, making the cooler twilight hours ideal for activity. The evolutionary benefits of nocturnal behavior were many. In a world teeming with predators, hunting at night meant fewer rivals and more opportunities to ambush unsuspecting prey. For smaller carnivorous dinosaurs, it also offered protection from the towering giants that dominated the daytime. Their senses adapted accordingly: larger eyes to capture faint light, acute hearing to detect movement in the dark, and perhaps even heightened smell to track prey by scent rather than sight. These adaptations mirror those of modern nocturnal animals, showing that the strategies of survival in darkness have deep evolutionary roots. Even herbivorous dinosaurs may have adjusted their behavior according to the time of day. Some species, vulnerable to predators, might have moved and fed more actively at night, using low light to conceal themselves. Fossil evidence from desert and forest habitats suggests that nighttime activity was not limited to predators alone. It was an entire hidden world, alive with sounds and movements that the daytime would never reveal. Understanding which dinosaurs hunted at night has also helped scientists paint a more dynamic picture of ancient ecosystems. The Mesozoic was not a static world of roaring beasts under the sun. It pulsed with life around the clock. When the great sauropods slumbered and the pterosaurs folded their wings, the nocturnal creatures emerged. Eyes glinted faintly in the moonlight, claws rustled through ferns, and silent footsteps traced paths beneath ancient stars. Modern descendants of dinosaurs, the birds, still carry traces of these ancient adaptations. Many birds today, such as owls and nightjars, have large eyes and advanced low-light vision, echoing the traits of their prehistoric relatives. This continuity across millions of years shows how effective nocturnal evolution has been, allowing certain lineages to thrive through vast environmental changes. The night hunters of the dinosaur age remind us that darkness was never empty. It was a realm of opportunity and quiet power, where keen senses and patience triumphed over brute force. Beneath the soft light of ancient moons, these creatures perfected the art of unseen pursuit. Their legacy lingers in the eyes of every owl, every stealthy predator that moves through the night, living proof that life has always found a way to rule both day and darkness alike. For much of history, dinosaurs were imagined as cold-blooded giants, slow, sluggish, and reptilian, basking under the prehistoric sun to warm their heavy bodies. This image persisted for generations, shaped by early comparisons between dinosaurs and modern reptiles. But as science advanced, that picture began to change. Evidence from fossils, bone structures, and even chemical traces has revealed that many dinosaurs were not cold-blooded at all. Some were warm-blooded, with metabolisms that allowed them to regulate their own body temperature, remain active in varying climates, and move with energy and purpose. This discovery transformed our understanding of dinosaurs from lumbering monsters into dynamic, vibrant creatures that lived and breathed with the pulse of life, much like mammals and birds today. The clue to this revelation lies deep within their bones. When scientists examined thin slices of fossilized dinosaur bones under a microscope, they found intricate networks of blood vessels and growth rings that told stories of high activity and rapid growth. Cold-blooded animals, such as lizards or crocodiles, grow more slowly and irregularly, depending on environmental temperatures. But many dinosaurs showed patterns more like those of warm-blooded creatures: steady, fast growth, sustained by a high metabolism. Some species reached full size within just a few years, an impossible feat for an animal relying solely on external warmth to power its body. Fossil evidence also suggests that certain dinosaurs were capable of living in cooler regions, far from the tropical warmth once thought necessary for reptilian life. In polar areas that experienced months of darkness and cold, fossils of herbivorous dinosaurs have been found, species that would not have survived if they depended entirely on the sun for heat. This hints that they maintained internal body temperatures, keeping themselves warm and active even when the environment grew harsh. Their physiology must have been far more advanced than that of typical reptiles. Perhaps the strongest link to warm-bloodedness comes from the connection between dinosaurs and birds. Modern birds are descendants of theropod dinosaurs, the same group that includes Velociraptor and Tyrannosaurus rex. Birds are highly warm-blooded, their bodies burning energy constantly to sustain flight, maintain temperature, and power rapid movements. The discovery of feathered dinosaur fossils in China provided not just visual proof of this relationship, but biological evidence as well. Feathers, after all, are excellent insulators, keeping body heat trapped, something unnecessary for a cold-blooded animal, but vital for one that generates its own warmth. The presence of feathers, combined with evidence of active lifestyles, suggests that many theropods were indeed warm-blooded, or at least partially so. Not all dinosaurs, however, fit neatly into one category or the other. Some may have been mesothermic, a middle ground between warm and cold-blooded. They could raise their body temperature through metabolism but did not maintain it as precisely as mammals or birds do. This would have allowed them to conserve energy while still staying more active than true reptiles. It's possible that this intermediate state was one of the keys to their success, allowing them to thrive in a range of climates and grow to immense sizes. The idea of warm-blooded dinosaurs also explains much about their behavior. Warm-bloodedness would have supported their agility, fast movement, and complex social interactions. Herding species could migrate over long distances, hunters could pursue prey for extended periods, and parents could tend to their young with the endurance that cold-blooded reptiles could never achieve. These were not creatures that dozed under the sun waiting for warmth. They were always in motion, alert and adaptive. This shift in understanding has brought dinosaurs closer to us in a sense. They were not strange, alien beings from a lost world, but living animals with energy and vitality, driven by the same internal fires that fuel warm-blooded life today. Their hearts pumped hot blood through strong muscles, their bodies burned food into energy, and their lives played out with speed and intensity. The ancient world, once thought to crawl with slow reptiles, now comes alive in our minds with the rhythm of movement, creatures breathing, running, and thriving with warmth within. In the end, the discovery that some dinosaurs were warm-blooded does more than change scientific categories. It brings us closer to them as living beings. It reminds us that evolution is not static but fluid, full of transitions and surprises. Dinosaurs, far from being cold relics of the past, were vibrant and adaptable, their blood running warm through the ages, their legacy still alive in every bird that takes to the sky today. Among the many astonishing creatures that once roamed the earth, few were as strange and captivating as Therizinosaurus. This dinosaur stood apart from the usual image of sharp-toothed predators or lumbering plant eaters. Its most remarkable feature was its claws, vast, curved scythes that could reach over 3 feet or about 1 meter in length. No other animal, living or extinct, possessed claws quite so long. They looked like weapons from a nightmare, the kind of tools one might expect on a monster designed purely for battle. Yet Therizinosaurus was not a bloodthirsty killer. Its enormous claws, though terrifying in appearance, told a story far more complex and surprising about adaptation, survival, and the hidden logic of evolution. The first fossils of Therizinosaurus were discovered in Mongolia in the mid-20th century, and at first, they left scientists completely puzzled. The claws were so gigantic and curved that paleontologists initially thought they must have belonged to some kind of giant turtle or marine reptile. Only later, after more bones were unearthed, did researchers realize they came from a theropod dinosaur, a group that included the fierce Tyrannosaurus rex and swift velociraptor. But Therizinosaurus defied expectations. It walked on 2 legs like its predatory cousins, yet it had a long neck, a potbelly, and broad hips more like those of a plant eater. The claws themselves were truly extraordinary. Each one was narrow and elongated, ending in a razor-sharp curve. Even without flesh or muscle, the fossil bones alone stretch over 3 feet, meaning the living claws could have been even longer when covered with keratin, the same material that forms human fingernails. They were not simple spikes or hooks, but elegant, scythe-shaped tools that could sweep through the air with both grace and power. For a long time, no one knew what such claws could possibly have been used for. The most likely explanation is that Therizinosaurus used its claws not for killing, but for feeding. Despite being a member of a largely carnivorous family, evidence suggests it was herbivorous. Its long neck and beak-like mouth were well suited for pulling down vegetation, and its claws may have been used to hook or rake leaves and branches from trees. It could reach high into the forest canopy, gathering food in ways that few other herbivores could. The claws might have also served to defend the animal from predators, slashing at attackers who came too close. In a world filled with toothy hunters, even a gentle giant needed protection, and Therizinosaurus was well equipped to deliver it. Standing up to 10 meters long and weighing as much as 5 tons, Therizinosaurus was an imposing presence. Covered in feathers, as many scientists believe, it would have appeared even larger and more unusual, like a giant, feathered bear with the arms of a nightmare. The claws added an air of mystery and menace, even though their true purpose was likely peaceful. They might also have played a role in courtship displays, with males perhaps using their impressive claws to attract mates or intimidate rivals, much as peacocks or birds of paradise use feathers today. What makes Therizinosaurus so fascinating is how its body breaks expectations. In a group of dinosaurs known for hunting and aggression, it evolved into a slow-moving plant-eater armed not with teeth, but with tools. Evolution, as it often does, repurposed old designs for new purposes. The claws that may have once been used by its ancestors to grasp prey became instruments of foraging and defense. In this transformation lies the beauty of nature's inventiveness, the ability to take something fearsome and turn it toward survival in gentler ways. Today, when people see reconstructions of Therizinosaurus, they often react with awe and disbelief. The idea of an animal wielding claws longer than a man's arm feels almost mythical. Yet those claws were real, shaped by millions of years of evolution and perfectly suited to their task. They remind us that in the prehistoric world, strangeness was not an exception but the rule. The Earth's past was filled with creatures that defied imagination, and among them, Therizinosaurus stood as a masterpiece of bizarre design. An ancient giant whose long, curved claws still cut through the mystery of time, inviting us to marvel at how life once found its many, unexpected ways to thrive.